So here's the room set up for the talk on arithmetic public key encryption. Next, in case anyone wants a link to the video that's being shot by our professional photographer Patrick, then just please put your email on this list, and the link would also be forwarded to you. Please include your credit card number and social security number. We'll just use these for record keeping. And our database is completely secured with our 3-digit password anyway. Nothing to worry about there. Us Maryland professors, we volunteer to do these presentations, but donations are accepted. And the reason that we volunteer to do these presentations is because we love the content and the idea of getting ideas across to people. It's got absolutely nothing to do with the fabrication that wear hams that light the spotlight. Notice the laughter in all the teachers' faces. However, we may provide the lecture, but we don't provide the room or the facilities. That's provided by the administration. Now, the difference between a teacher and an administrator is that an administrator is in touch with reality. They view this as a marketing opportunity to increase enrollments. And as such, they provide freebies, as you see here on the table. And in fact, it was even more pronounced earlier before austerity set in, and we actually had a whole table full of peaches on the back. But of course, this led rise to the fear, especially on the part of the faculty, that some of the students were merely coming because of pizza. Totally groundless, of course. 2 years ago, I gave a talk on the Higgs boson, and there was a journalist, quite a few actually, for one reason or another. And there was a journalist there who felt that the talk might have been over the heads of the audience. So he did an exit strategy, exit polling the way out in interviews, and he asked one audience member, what are you taking home from this talk? And he said, 2 pepperoni and 1 double cheese. So that justified our fears. To get on to the topic, what we're doing tonight, which is encryption, public key encryption, everyone in this day and age right now is pretty sure that you need to encrypt sensitive information before you send it out over the internet. And until we recently had, and recently I mean 1977, recent for me, had public key encryption available, then we only had a mode of encryption in which you encrypted the message you were going to send with one key, and you had to send that same key to the person that was going to decipher it, which means the key also had to be transmitted and could also be intercepted. It's called symmetric key usage, and it was very, very unsatisfactory. So the difference between public key transmission and the older types is that the public key is not the same key that is used to decipher the message. The key used to decipher the message is totally kept in private. So when I first came across this idea, I said, that's ridiculous. If there is a key that is used to encrypt a message, then the same key must be able to decrypt the message, and I simply didn't believe it. So I went around for a few years not believing it, and finally a few weeks ago I decided to look into it. And I found out that I was right and wrong at the same time. So it's been intriguing to see how those two fit together. Now, I teach a couple of courses. In particular, this spring I'm going to teach IFSM 201 and IFSM 300, which are Introduction to Computers and Introduction to I'm going to teach this, Information Systems. It's been a couple of years since I taught it. And in those courses, both of which I've taught now for Maryland for about 82 years, we always come to a certain point in the course where we touch on public keys. And in the textbook that I'm using, no matter which one it was, it always says that the actual way that public keys work is at a more advanced level than this course. And that's all it's ever said about it. So I took a look at it, the way that we all take a look at things. I went to Wikipedia, and after about 2 days of deep thought, people says, you okay, Tom? You okay? But they usually do that anyway. And then I understood how it was done. And I realized that it was not complicated at all, that it didn't deserve its reputation. And it's very, very easy to understand, as you're going to find out in about 20 minutes. And as some students are going to find out next spring also. So let's get started. Let's suppose that you want to send a message, and over here we have what looks like a whiteboard, but it's very clear that it's a computer. And the computer has an invisible side that's only visible to the operator of the computer. And then when he sends something out via email, it's visible, of course, to the whole world that can intercept emails, which is everybody now. So he's working on his invisible part, and he decides on the message that he wants to send is a simple word, hello. So he moves it over to his visible part, where it's transmitted across to the receiver. So the receiver picks it up on his email and moves it to his internal private space and reads the message hello, and the transmission was totally successful. Absolutely no problems. The only real disadvantage is that along the way there was a bad guy. And he also picked up the message hello. And that's something that you didn't want to happen. So you say, well, that's no real problem. What's the problem with this guy picking up a message that's saying hello? And you say, that's no problem at all. But there's a possibility I could have been sending some data that was much more sensitive, in which case I would not have wanted him to pick it up. For example, suppose I was sending a message that would have completely revealed my identity to anybody that was interested in identity theft. For example, suppose I was sending my favorite color. I would certainly want to have that encrypted. So I'm going to take as my favorite color, violet. This isn't actually my favorite color. You didn't actually think I would tell you my favorite color, did you? And before I send this, I realized from my experience with hello that I have to encrypt it. So in order to encrypt the message, you need two, an encryption scheme. And the encryption scheme I've chosen is the simplest one that's ever exists. It's called alphabet forward. I created it 2 weeks ago. Nothing could be simpler. I'm sure it exists already. And in order to use it, you need to have a key. So besides the message that we want to encrypt, we need to develop a key. Now the key that I've chosen is the 2-digit key 65. And the way that I use this key, my structure, is I write it under the entire letter, message, and I repeat it until I come to the end of the message. Now in actuality, my message will be a huge document with thousands and thousands of words in it. And in actuality, my key will be a 50-digit number, not a 2-digit number. Would you prefer me to use the 50-digit number? Well, thank you. So I'll go along with a sample 2-digit code. Now the way that alphabet forward works is that I take the letter in the alphabet and I forward it that many. So to make life easy and to save myself and you from embarrassment, I put the alphabet on the board, and we can take the letter B and we just advance it 6 places. 1, 2, 3, 4, and we loop sometimes. So we go to the end of the start of the next alphabet and we come to A. So this letter gets encoded as an A. And quite similarly, the letter I, if we advance it 5 places, 1, 2, 3, 4, 5, becomes in. So this alphabet forwarding enables me to produce the encoded word, and the O becomes a U, the L becomes a Q, the E becomes a K, and the T becomes a Y. So now I forward my encoded word to my visible section, and I send it, And it's received by my receiver, who receives it and then moves it into his private section. So he also has now ANUQKY. And of course the bad guy picks it up. Now we don't worry about this because it's totally indecipherable, agreed? Because we've encrypted it. So we feel really smug, safe, and secure until we get a message back from our receiver that says, that's your favorite color. I can't make any sense of it at all. And you say, of course you can't, because I encrypted it. Well, would you mind sending me your encryption key so I can decrypt it? So he says, not at all. So we send over the 65 that we used to encrypt it. It comes over to him, and he puts the 65, because he knows it's alphabet forward, we shared that, and he goes backwards. When we went to the right in the alphabet, he just comes back to the left, and he produces violet. And he says, wow, it worked. Violet's your favorite color. But I can't remain friends with someone that has a favorite color of violet. Relationship over. So it worked, but it didn't work. So the bad news, of course, is that the bad guy now also knows that your key is 65. And because he knows that your key is 65, he can also reverse the encoding. And he also gets the violet. So it didn't work to send your key straight forward. So the next step in sophistication is that not only have you encrypted the message by using a key, but now you have to also encrypt your key to keep the bad guy from picking up the key, being able to decrypt your message. So you need a scheme for encrypting your key. Now a very simple scheme is called 9's complement. You take your key and you subtract it from a string of 9's. And it's called 9's complement. So what would your encrypted key be now? 34. So lo and behold, you read 34 out to your public area, and you send it across to your friend, and he receives the 34, and he says, thank you very much for the 34, and he moves the 34 in, and he tries to decrypt using it, and he produces nonsense because he didn't know the scheme by which you encrypted it was 9's complement. So he's still missing that information. And of course, the bad guy picked up the 34, and he also can't make any use of it because he doesn't know how you arrived at the 34. What was the algorithm that gave you the 34? So your friend calls back to you, what was your algorithm that you used? I need to know to encode your key. So you very quickly tell him, well, I used the 9's complement. Oh, we used the 9's complement. Well, 9's complement is reversible. It's very easily reversible. If you start with the 65 and you do a 9's complement, you get the 34. But if you take the 34 and just do a second 9's complement, you get back the original. So the 9's complement is totally reversible. So as soon as it's known that you produced your encryption key by a method of 9's complement, then not only can your receiver decrypt your encrypted key and get back the original key and use that in the message, but so can the bad guy. So this is a head-scratching point that we're in 1977. You remember it? I remember it. When we had this process that no matter what we did to the key, we had to communicate to the receiver what we did to the key. The bad guy can pick it up, and he could do the same thing the receiver could. So everybody is stuck because what we needed was a method of encrypting the key that is not reversible. Let's take some of the common reversible operations that we could do on the key. Suppose the key is designated by X. If we hide the key by multiplying by 3, so this becomes our encrypted key, could not that be reversed by dividing by 3? So the operation of multiplication is easily reversible. If we hide our key by adding 3 to it, can't that be reversed by subtracting 3 from it? So we need an operation that we can do to our key that is not reversible. So enter now the operation called modulus. not reversible. Therefore, it's entirely suitable to use for a key that you do not want the bad guy to be able to reverse. So I'll give you examples of what we mean by modulus. 27 modulus 5 equals 2. 13 modulus 2 equals 1. 11 modulus 3 equals 2. Those of you that have either seen this before or fairly quick realize that what I'm talking about is the remainder. Modulus is the remainder that's generated. If you divide 27 by 5, the remainder is 2. So 27 modulus 5 is 2. If you divide 13 by 2, the remainder is a 1. So let's try one of these hard ones. 27 divided by 5 goes 25 times, and lo and behold, the remainder is 2. So this 2 is the modulus, 27 modulus 5. So let's see if you can do one or two of these. 39 modulus 6 is what?
3.
3.
3.
3? Okay, good. Now, this has been abbreviated as 39 mod 6 instead of the word modulus. Now, I've never approved of the word mod. And those of you who know me well can understand why. And those of you who know me well also understand that my opinion was never asked for. So they went ahead with mod. Simple mods we don't have any real hard to do. So please tell me, what is 1312 mod 211? I can do it. Because most calculators, at least the one I'm using right now, come with a mod key. And you can identify the mod key because it has MOD on it. So let's make use of this mod key.
46. 46. I didn't use my calculator.
Well, it's 46. As I told you, I had a calculator on this side of the room.
211 times 6 equals 1266. The remainder is 46.
Okay, so 432, what does that say?
9672.
9672. And I press the mod key, and I want the modulus of
1392.
Okay, go. 552, that's what you got, right? So you can make use of the mod key on your calculator, or you can ask a bright student to generate certain modulus for you that you might not be able to do yourself. Let's check them on this one. 1312 mod 211. You maintained a 46, right? And he's totally confident.
You need to read. You need to clear. You need to clear it.
1312 mod 211.
You need to clear the calculator first.
What was I going to catch him? 1312 mod 211 equals 8. And I have to put up with him twice a week for 7 days. Okay, as he says, it's 46. So now we understand what mod means, and you see, for a reason that I'm about to indicate, that mod is a perfect way to hide our key. Because if I give you the following information, first let's look at some series of numbers. So 7 mod 5 equals 2. 12 mod 5 equals 2. 17 mod 5 equals 2, etc., etc., etc. 97 mod 5 equals 2. How many numbers have a modulus of 2? An infinite number of numbers. If you mod 5, you'll get a 2 as mod 5 to that number for some infinite number set of numbers. So if I take my key and I hide it in the following way. I take my key and I say that my key mod 5 equals 2. I've certainly hidden my key, agreed? Because the bad guy picks this up because you send it that the key mod 5 equals 2. From this information, can he go backwards and get the key? Because how many possibilities are there?
Infinite.
Infinite number. So he cannot go backwards, can he? So as soon as I hide my key by taking a modulus with some base number, it becomes irreversible. And that's the secret of public key encryption. That we hide our number by taking its modulus with some base number, such as 5 in this case, and as soon as we do that, it could be any one of an infinite set of numbers. And the bad guy cannot decipher it in the slightest way. So that's exactly the solution. The trouble is, as you can see ahead, is that as soon as it gets over here, this guy has exactly the same problem. That all he knows is that the key mod 5 is equal to 2. And if he could solve that equation, then he could go backwards into your encryption. But he has exactly the same problem as the bad guy. There's an infinite number of possibilities. So the solution to the problem is that before you send out your key and take the modulus, you raise it to a certain exponent. Now this little e is called an exponent. I'll give you an example. 3 to the exponent 2 is a 9, so the 2 is called an exponent. So we're going to create some exponent that if you raise your key to this exponent and take its modulus, then the number that comes over here is going to be your encrypted key. Your encrypted key becomes a 2. This is how you encrypt it. You start with your key, you raise it to this power, you take the modulus, and this becomes your encrypted key. And now the bad guy is even worse off than he was a moment ago, because he could not tell what your key was just by knowing the mod 5 was 2. Now if you've raised your key to some power before you took the modulus, now his job is even harder. He can't figure out what it was. The reason it improves the abilities of your receiver is that this exponent was very carefully chosen by the receiver. He chose it in just such a fashion that he has a magic number. And only he has it. He has a private exponent called D. And if he takes your public exponent, your encrypted exponent, in this case 2, and he raises it to the power D and does another modulus, then he's going to get back your original key. I'll give you an actual numeric example. Let's take this key 65 that you want to encrypt with this modulus technique. The process starts not with you, but with the receiver. The receiver chooses what modules will be used. He makes that choice. The receiver, before any message is sent to him, he creates his public modulus and broadcasts it to the whole world. And in this case, we're going to create a at 3233 as our public modulus. Going to send it to the whole world. Next, she creates a public exponent, which she's also going to send to the whole world. In this case, she creates the public exponent 17. This is now visible to everybody. Everybody knows if you want to send him an encrypted key, you use the exponent 17 and you use the modulus 3233. That's the rules of the game. So let's apply that to our 65 and encrypt it. So to encrypt 65, we take the 65, which is our real key, and we raise it to the public exponent. What's his public exponent?
17.
17. Then after we do that, we take the modulus of the public modulus. What's the public modulus?
3233.
3233. And this becomes our encrypted key. So, Jose, what's our encrypted key going to be? Okay, let's do it on the Windows calculator. So the first thing that we have to do is take our real key, 65, and we're the only ones that know the real key. It's invisible. We take our real key, 65, and we raise it to the power of 17. And we see what number that produces. A relatively small number. Now this is the reason that even though the bad guy knows exactly what you're doing, he knows that you are taking your key, which he doesn't know. He knows you're taking it to the 17th power because that's public. And he knows that you are then taking modulus of 3233 because that's public also. And the reason that he cannot work backwards is because that number is so big that if he tried to guess what your key was by all the possibilities of that number, it would be 10 to the 211th power years, which you're willing to wait for. So you're safe by numbers in this case. So let's finish the encryption. We have taken 65 to the 17th power. So what's the next step?
Mod
Mod what?
3233.
3233. Mod 3233 is 2790. 2790 becomes your encrypted key. So you send it out as a 2790. So your encrypted key is known to be 2790. And you send it out, 2790. So this is what you broadcast. You broadcast your encoded message, and the key is 2790. The bad guy picks it up, and he knows that how you got the 2790 was by this equation. But can he work that equation backwards? It's a modulus equation. It has no backwards. So he can't go backwards. So the only thing he can do is try to guess your key one number at a time and see if it fits this equation, which he can do in 30, 40 years with a very fast computer. So you're not worried about that. Because in actuality, your key is 50 digits long. And because your key is 50 digits long, then by sheer guessing, he cannot guess it in a practical amount of time. The only thing he can do is reverse his equation, but modulus equations are irreversible. So he loses. Now the only thing left is how does your good guy win? Because your good guy has a magic number. He has this magic number, D equals 2753. I'm going to show you in a couple of minutes how he created that magic number. But because he is the only person in the universe that has this number, he is the only person that can work that equation backwards. If you don't have this number, you can't work that equation backwards. If you do have this number, you can work that equation backwards. So this is a secret number, very private. Everything on this side of the line stays home. Let's see what happens if he takes the key that you sent him, which was 2790, raises it to his private exponent, 2753, and then one more time takes the modulus of 3233. Well, that's a fairly large power. Let's see if this computer can handle it. I haven't tried it yet. 2790. And I'm going to take it to the power of 2753 and see if it will multiply it. And it did multiply it. Notice the exponent. It's only 10 to the 9,485th power. So good luck for the bad guy trying to count up possibilities, true? We're not worried about that. But now let's look at the magic that happens if I take a modulus 3233. Modulus 3233. Bingo. End of magic. Original key recovered, true? And untouchable by the bad guys. So the original key is recovered, and the bad guy couldn't have done it without this magic number key. So with the original key in place, I can change this back to violet. So the key 65 has been transferred to the receiver. The key 65 has been taken to a public exponent. It's modulated by the public modulus, which creates an encrypted key. The encrypted key is transmitted safely because it cannot be reversed, even if intercepted. When it arrives back to the person who originally created the public parameters, he has a magic number. And his magic number is capable of reversing that equation and pulling back the original key. So now I'm going to work through one example with simple numbers, showing all the steps in the order in which they actually happen. Then I'm going to sit down, and you guys are going to create your own public exponent, public modulus. You're going to create your own message. This has got a white face. And you're going to create your own key. You're going to encrypt your key. You're going to send it out, and you're going to decrypt it. So what you're going to do in 5 minutes is everything that I'm going to do now in an example. Now, the first thing to know is that this public modulus, which is the first number that goes public, was not picked out of the air. It is not any random number. It was chosen in the following way. To choose your public modulus, you pick two prime numbers, P and Q, and you multiply them together. And that gives you your public modulus. It's the product of two prime numbers. Now, let's remind ourselves, what are the prime numbers? 1, 3, 5, 7, 11. Those are numbers that can only be divided by themselves and 1. 1, agreed? So now, let's continue your expertise. Class, what's the next prime number? 13. 13, next.
17.
A different person.
23. Oh, 19, 23.
Okay, those are all the prime numbers left less than 30, agreed? So from that list, I'm going to pick a P and a Q. Now, this particular public modulus that we used a moment ago was found by P is equal to 61 and Q was equal to 53. Those are the two prime numbers that were picked. And if you multiply those two together, then you will get the public modulus. But I'm going to pick some simpler numbers. And the two numbers I'm going to pick are that P is 23 and Q is 29. So all this is done prior to anything else happening. There's no published exponent, there's no published modulus. This is the first thing that's done, and the receiver does it at his own whimsy. He just picks two prime numbers. Now, in general, each one will be maybe 20 digits long. Very, very large. But still, there's tables of them, and not hard to find. So he picks two of these, and the public modulus is going to be the product of those two. So now, who wants to tell me, calculators encouraged or permitted?
767.
One more time?
He says 767.
That's right, 667. Want to check it?
It is.
667.
I think I added 100 to that.
Okay. So this is 667. So now that he's chosen his P and a Q, which he keeps very secret, he's the only one who knows the P and the Q. But the N, the public modulus, was not picked out of the air. It's formed as a product of two prime numbers. This is necessary for it to work. He picks the two prime numbers and keeps them secret, and now he forms his public modulus, which is 667, and releases it to the world. So when we say that this man creates a public key, it's a little bit misspeaking. What he creates are parameters that are used to create by the sender a public key, his own key. So this man shows the world the parameters that are to be used by anyone that wants to send a message to him. He doesn't create their key, they create their key. But he gives them the two parameters by which they will create their key. So the next thing he has to do is create his public exponent, which we call by the letter E. That's also done by very specific rules. Now we come to a very hard part of the calculation. Can someone please tell me what is P minus 1?
22.
You done this before? What is Q minus 1?
28.
But I'll get you that one. So now what is P minus 1 times Q minus 1, Jose? Anybody?
22 times 28.
616. This is known as your private modulus. It also stays behind the wall. You cannot show it to the world. Now you're about to create your E, which you're going to show to the world. Your E can be any number at all that does not have a common factor with 616. So you're free to choose that number, as long as it doesn't have a common factor with 616. So the easiest way to do it is to pick a low prime number, make sure it doesn't divide into 616. So I choose a number
5.
13. You can choose yours in a moment. Now, 13 is prime, agreed? So it doesn't have a cofactor. Now, the only thing is, can it, because it doesn't have any factors. The only thing is, does it itself divide into 616 evenly? Answer, no. So it's qualified to be our public exponent. So now that we have chosen our public exponent and public modulus, we're open for business. Anybody can now encrypt their keys. And this guy over here will do so. He will now encrypt his key according to the new public parameters. So it's a 65 to the 13th power, modulus what?
667.
667. So this is his new encrypted key. Does anyone want to punch it in on the computer, or? This is a historic moment. Jose is using a computer. 65 to the 13, mod. No, start. Okay, go. Keep going. You're faster than me. Well, that's one of our fairly small numbers again. Agreed? Easy to work through. And modulus 667. 605. So this becomes the key that you now identify as your encrypted key, and you send it back. 605. The bad guy looks at it. He knows that what you've done is you took your real key and you took it to the 13th power and you modulated 667 and you produced a 605, but that doesn't help him in the slightest to get your real key. It's impenetrable to go backwards. This guy is going to get your real key if only he had his private exponent D. This is how he finds his private exponent D. This is why this public key algorithm took so many centuries to discover. It's not at all obvious how he should calculate his D. So now I'm going to share this with you. Sorry, excuse me about that. You guys are now on the inside. You're now going to know how to get these private exponents. Go. They come by the following prescription. D is equal to 1 plus k times the private modulus divided by the public exponent. Now you can say, where did that come from? Well, there's a little bit of math involved in where that came from. It's also not very hard to understand, but for the moment we will just take that as being true. Now, the rules are that D has to be an integer. And the other rules are that K has to also be an integer. Not hard to follow. So that means D is equal to, which is an integer, 1 plus K, and what's our private modulus? 616, and this is also an integer, divided by 13. So what we do is we make a table for all the possible values of K, and the D's that they produce, 1 plus K, 616 over 13. Now, what's the maximum size of our table? It's going to be 12. Because if you continue to increase the number until it divides by 13, you only have to increase that number by 13 and it will divide, because you've included 13 into that number. So we only have to examine 12 Ks. There will be one of these. So let's take them one at a time. The first one is K will be equal to 1. So Jose, punch in 1 plus 616 and divide 13 and see if it comes out even. If it comes out even, we're done.
Divided by 13.
Yes. Tell me what you get.
48.38.
617 divide 13?
You said 1 plus 6,
1 plus 616 is 617.
right?
Divided by
13.
13.
1 plus 616
It is.
divided by
13. It is 47, 46. So that didn't work because it didn't come out to be even. D will be the first integer we come to. Let's try 2. So what is 2 times 616 plus 1 divide 13?
2 plus 616 or 2 times?
2 times. 2 times 616 plus 1 divide 13.
plus 1
Plus one.
Plus the one, I thought it was, okay. So 2
times 6 ones
66
plus 1
plus 1.
divided by 13.
You gotta do the division after you add the one.
Well, that didn't work either. Let's try 3. 3 times 616 plus 1 divided 13. Okay, let's try 4. 4 times 616 plus 1 divided 13. Okay, now I'm going to let you take all the glory. You try 5 all by yourself. Bingo. We found our private exponent. It's the first integer that you arrive at in this table without a decimal part. So we have found 237. So we have found our private exponent, 237. And this is how we finish off. We take his encrypted key, 605, we raise it to our private exponent, and we take modulus 667 again, and we reproduce his original key. Try it. 605, his encrypted exponent,
Exponent.
to the private, his encrypted key to the private exponent 237, modulus 667, that's a pretty big number. Modulus 667.
Bingo.
I wish I could say that I did this. But in truth, Wikipedia did this. Okay. So now, does the bad guy have any chance of recapturing the 65 without knowing these numbers? Without knowing P and Q, which gives him P minus 1, Q minus 1, which gives him the 616, which he needs in this equation. The only thing that he can do is take this public modulus and try to find 2 prime numbers that would multiply it. And this public modulus is 55 digits long. And if he tried to work through all the possible prime numbers that could have been multiplied to produce it, then he's going to be passing it on to his great-great-great-grandchildren and still not having it done. So because this public modulus is so large, it cannot be found the 2 factors that created it, which are both prime. If he had these, he could do the rest himself. But he's never going to find the P and the Q because the numbers are so large. And because the numbers are prime, he can't bootstrap his way along by dividing by a 2 or 3 or 4, because none of those numbers will divide prime numbers. So he has to guess the prime numbers himself, and he never will. Sir, question?
So being that those numbers are technically static because they're selected at the beginning, I understand if he's only using one PC to attempt to crack this code, and let's just say he bots 1 million PCs to perform this calculation,
Yeah,
he has a higher, greater chance.
that's right. That brings the time down to 93 years. So with our fastest supercomputers today, it's not at all possible to step your way through guessing, to do this by guessing, because of the sheer size of the numbers. And if our numbers were only of this sort, 2-digit numbers, then we could perhaps not guess our way through individually, but we could easily program a PC to break this by guessing all possibilities within an hour. No trouble doing that. But the numbers that we use in actuality are 10, 20, 30 times larger than the numbers used in this sample. So now what I'd like to do is to prepare you guys for your t-shirts saying, I am a public key practitioner, by having you develop your own public exponent and public modulus. And after you develop them, I want you to publish them. And after you publish them, I want the center's team to pick up the published ones and to encrypt their key, which they will choose for themselves. And then I want them to publish their encrypted key for you to pull it back and to decrypt it using your D. Josh, this is your team. You guys are the receivers. Mitch, you guys are the senders. Now what I want you guys over here to do is first, you're going to pick your own message. Not my message of Violet. And it must be at least 10 characters. And you can include spaces if you want, because we have spaces in here. Okay? Then I want you to pick your key. I chose 65. You can pick a 2 or a 3-digit key. And then you write it under your message. And then you go to the really hard part. You have to alphabet forward. Be sure you get agreement on this. And you produce your encrypted message, which you put in your visible set. Then you wait for your receiver to publish. There's public exponent and public modulus. Once he publishes these, then according to this prescription, you encrypt your key and also make it public. After you do that, your part's done. Then they have to pick up your published encrypted key and put it into the reverse formalization, taking it to the D power, one more modularization, producing your original key, and then they will apply that in alphabet backwards to your encrypted message and tell you what you say. So you guys can start anytime you want. Jose is an adept calculator operator, so you need him. You start by picking your prime numbers, remember? Now, there's one thing to be sure that doesn't happen. Reverse is 180.
If I got a piece of paper?
Yeah, so I was gonna ask.
You guys want to do this in paper first? What?
Oh, yeah, yes.
Okay, so now nobody knows what you're doing. Nobody knows what you're doing, and all we want you to put here on this front board is your encrypted message and your encrypted key, right here. You're all done. So write your message, and write your message, choose your key, encrypt your message,
Oh, we gotta know
and you
there.
will write your
Oh, no,
encrypted message.
So we gotta capture the codes and,
And then when these guys are ready, you encrypt your key. By the way, you guys choose prime numbers under 30. Choose your prime numbers under 30. And choose your exponent under 15. Make life easy. Actually, choose your exponent under 11. I will. Oh my God! Even I would not stoop that low. That's ridiculous.
So it's basically 3, 5, 15.
Now you have to play this table game. Remember the table game over here? You need to do the table. First you need E. Now E is any number that's not a cofactor of that. No, it's not a cofactor of this, that doesn't matter. So now you can publish, and you can go like work. You can give them the 35.
So again. Oh, I thought we had that. Yeah, and.
so we can give that to them, so.
We need now an 8. Come up with, so we need to do 1 plus.
You need to do those calculations.
1 plus
So
K.
we, I guess we're using certain. So, yeah, that's like right on, which is 24 plus K.
Encrypted message, okay, here we go.
There's H, Y, C, is that a U?
Yes.
K, T, Q, J, C, M, R, what's after the R?
RRH.
That two R's?
Yes.
Okay, the second R doesn't look like the first R.
Picky, picky.
Okay, so there we are.
Okay, but we'll have to.
We gotta get their number.
Remember how to make yours?
No.
Okay, yours is your key,
Reverse of that.
E on N. So it's going to be, whatever your key is, and that's your secret, I don't want to know it, it's going to be to the 7th power mod 35.
So ours is public, that's why it's visible. Theirs is privileged, so that's why it's hidden to them. That's why when, I think when you publish your key, if you only publish.
Yeah, there's some public
your
key.
Right, get it.
They're different. When you, I think when you, like, so disclosure, like email encryption, yeah, they're public ones.
Right.
Now,
That's why you gotta,
we usually have like 3 keys, a private one, a public one, I forgot what
the digital signature.
Yeah.
No, that's where it's backwards, it's just backwards. Digital signature is the same mechanism in reverse. That is, you release your private key and keep your public.
Yes.
They're different.
That's right, because the private is what they need to decrypt.
Okay, they're claiming that their encoded key is 0. Because yours is encrypted, right? So unfortunately, they did break one of their rules, and that is that the key that they choose has to be less than your in. That's never even really stated, because your in is usually 1 trillion digits long, and their key is usually less than 8. So, but that does have to be true. So they can either choose a smaller key, or you can choose a larger in. I would suggest you choose a larger n, since this was really childish.
Way to go.
Good luck.
Like
11.
All the calculations in first time.
11 and 13.
Inside your desk.
I understand that.
And for your E, take a 9.
He stole the marker. Yeah, he stole the marker. Wow, did that record?
Yes. It did. 11.
13, 10, 12.
120. And I think at 9, it doesn't factor, goes at 1. No, it's just 9. Okay, now redo.
It is 143.
Okay, they have a new N. They have an E of 9, and his N is 143. So you can you keep the
Now you guys have to recalculate D.
You know,
Fun time.
So we've got K up to 8.
so no. That's not even. 241 divided by 9.
No, I need the
No,
number.
it is not even. 1 and 2 don't work.
Is that 1?
No, it's not one.
No, 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 what was the number for 1?
It just didn't work.
Okay.
That's nice. That looks like
Do I
it.
put your number in
Yeah. Yeah. Well, no, right under it now.
Oh.
Key to the 9 mod 133 equals 7. Hi, bingo. We just put an X in the numbers. Okay, we're getting very close. Only a few left.
It's gotta be in the, no, it's
There's 1 through 8.
That should be 721 divided by 58.
Okay, keep going. No, I still say it has to be less than 9.
Well, see if I miscalculated someplace.
Want to redo?
Yeah.
Aye.
That'd be a 10.
Oh, look at this, guys.
Rule.
E
What if you do wrong?
and this cannot contain common factors.
Three. You shouldn't have picked a 9.
Aha. Concur.
Yeah, you do.
10 works.
So,
Just do 7. Aren't you just gonna?
Well, 7 works.
Can have a common factor. So, let's try, that's a different number that doesn't have a common
Yeah,
factor.
because we have to.
5,
Oh,
right?
that's
Right?
Yeah, I can't do
not
it.
5.
5 has a common factor. 7?
Seven works.
Okay, pick a 7.
So next one is 7.
Yeah.
Good. Rules, rules, rules.
So we still got the 120.
Still got the 120.
Divided by, so what's our number on stuff?
7. Yeah.
It's not 1.
1728.
So.
17.28.
Or 1?
2 works.
2?
Yep.
What's 2?
Make sure I did that right.
So it's 2 times 120, which is 240 plus
240.
1, which is 241. Divided by 7.
Oh, it doesn't work. I screwed up someplace in the calculation. 361. Did I do 1, 5, or 6? So we're at 1,
1421. 1420. 14 is 20.
So it's 7.
20.
7.
Stuff that I didn't trust you doing.
Oh, it's okay.
Oh, there you go.
Right there.
Which one was that one?
6.
6?
Okay, tell 'em.
103?
Yeah.
Nice work, guys.
Do it again. Check it. That's
Okay,
right.
6
721 divided by 7.
plus 1. Divide 7.
Yeah.
And okay, 103. So now they've got their encrypted key. So here's their encrypted key.
39.
139.
Okay. So 39 to the 103? 139. 139. 103.
Yeah, I'm gonna send that to you.
Mod 143.
Where did the 220 come from?
Figure out
Yeah.
what it says.
Huh?
We got 35.
35.
139
Yeah.
to 103.
Yeah.
Mod 143.
Yep.
35?
35. Are we right?
Yes.
Yeah.
So now,
Huh?
We gotta find the message.
I know what the numbers, right?
The kids can do the rest.
Oh.
Yeah.
No.
Well, I don't know about backwards.
ET goes home?
U5.
U5. T5.
Yeah, question two, because
Home, K3.
three bits.
H. T5.
Little fortune, yeah.
Yeah. So, ET phone home.
That's confirmed.
C3.
Okay. Great work, everybody. Go home, you're done. Nice job, all around.
See, I told you this one.
I don't know if there's any interest in this. I prepared it, and I planned on doing it. It was about 45 minutes ago. And then I decided 15 minutes ago to give you a choice. And then given the state of exhaustion that we've all arrived at, and flipping through these possible rule violations, of which we made two, I made two, then I decided just to call the night right here. But given that the fact that nobody's running out the door, I'll restate what part two of the evening could be. You guys are now practitioners, like evidently, you can pat yourself in the back. You can prepare private exponent, public exponents, you can prepare public modulars, you can pass them on. People here can prepare their key to their encryption, and they can encrypt that key using your information, send back the encrypted key. You can prepare your private exponent successfully, which you can use to recover their key, which you can use to decrypt their message. So congratulations on the practitioner's part. Now, is anybody interested in seeing why this is true? Not just how to do it, but why is it? But first what I'm going to do is declare a 5-minute break in which anybody that doesn't want to see why it's true can sneak out. And then in 5 minutes we'll reconvene, and anyone who wants to see why it's true can see why it's true.
So that means there's like 5 pies coming on the way, right?
5
5 pies.
I don't speak.
We're still looking for the pizza pies.
They're from New York. This is limited enrollments. Limited enrollments produce limited snacks. I want to do it because I want to get it on tape. So I'll do it to an empty room. You don't have to stay, sir.
Okay.
Right. I'll do it to an empty room, maybe not tonight, but another day. So it doesn't have to be. Thank you. That was interesting. Pleasure, sir. You contributed. That's right. Or if you want, I can schedule another session for this. It doesn't have to be in this room with snacks. But we can keep the momentum going and doing it right now also for the 4 or 5 or 6 people that are interested. Hi, Richard. Come on in.
Hey.
Well, depends on how you interpret military times. 1730 or 7:30. Hi.
Thank you.
Pleasure, Kimmy. Okay. Now, if you guys are keen and guys is coming back, that's sufficient quorum for me to present the how it works. So I'm on for doing that. So your presence will be sociable. And if you understand the second part without understanding what you've missed, then I'm going to nominate you for Nobel Prize.
Well, this looks like it's not for the math challenge.
It's a challenge. Let's just say it's a math challenge. And it's basically, it's just arithmetic, but it's a bunch of it. There's nothing in here that you don't know by 7th grade. But it's just used.
That's not true. They don't teach you modulus.
You didn't know modulus in 7th grade? Where'd you go to school? Nothing. You knew it as remainder, right?
Yeah.
You have remainders. Okay, there it is. So it's just so much of it, and it's so intricate. It is fairly intricate. You make one rule violation and it's garbage. We found that twice. But as long as you obey the rules, it comes out right every time, all the time. And that's absolutely amazing, that it comes out right every time, all the time. So Now I can present to you why it comes out right every time, all the time, now that you know how to do it. But and my good marker is here. Okay, so break is finished, and we're ready to take off. So once again, feel free to leave anytime you want. This is just a reason why everything that you did for the last hour and a half will always come out correct and true. It's founded in what we call mathematical theorems or proofs. They're really just arithmetic. All the arithmetic is quite simple. So what I'm going to do is build a little toolkit of the arithmetic that we're going to be using. So the first is, if I have a number r, and I take the modulus of that with p, and if I have the sum of two numbers, r plus s, and I take the modulus of p, after I do the addition, it's equal to r mod p plus s mod p. In other words, you can take the modulus first and add them together, or you can add them together and take the modulus second. And in case this turns out to be bigger than p, you have to do another mod p at the end. So let's illustrate an example of this. Let's take 7 plus 4 mod 2. 7 plus 4 mod 2 is going to be a 1. True? 11 mod 2. I'm claiming that's equal to 7 mod 4 mod 2 plus 4 mod 2. And then after I'm all done, I take another mod 2. So what's 7 mod 2? 1. What's 4 mod 2? 2. And 1 plus 2 is 3. And what's 3 mod 2? 1. So we come back to it. So this is that the remainder of the addition is the addition of the remainders.
I'm confused on the 4 mod 2. Shouldn't that be 0?
Yes. Thanks. The only one who's tracking me honest. So that we don't need the extra step even. We just have a 1, and a 1 mod 2 is still a 1. Well done. Now the addition, the multiplication. If I have r times s, and then I take mod p, it's the same as taking r mod p first, and s mod p, r mod p times s mod p, and then we take another mod p in case this turns out to be bigger than p. So let's take an example. We'll use our 4 and our 7. They're very pleasant numbers. And that is that 7 times 4, say, mod 5. Someone calculate that one. 3. I'm claiming it's equal to a 7 mod 5 times a 4 mod 5. And then I do another mod 5 if I have to. This comes out to be greater than 5. What's a 7 mod 5 is a 2 or 3?
So 1
And 4 mod 5 is a 4. So we get an 8 and an 8 mod 3. 8 mod 5 is back to a 3. So the product, the modulus of the product is the product of the modulus. The modulus of the product is the product. And this works for powers because if both of these are r, you get r to a power. So if you have r to some power, and then you take the modulus of p of that, then it's the same as taking r mod p, and then taking the power, and doing another mod p if you have to. take a, say, 2 to the 6. 2 to the 6 mod 10. 2 to the 6 is 64, agree? 64 mod 10 is a 4. So I'm claiming that's the same as 2 mod 10 raised to the power of 6. And then I take another mod 10 if I have to. So 2 mod 10 is a 2, agree? And 2 to the 6th power is a 64, and 64 mod 10 comes back to the 4. So this is the same as the one above it. Instead of having a different factor for the second factor, it's just more of the same. So r to a power mod p is the same as we take the mod of r and then take it to the power later. The next one that we're looking at is called the Chinese remainder theorem. For reasons I'd be intrigued to know if anyone ever came around to telling me, but you're going to understand that it's true just by your real life experience. Suppose that you run around Okinawa Island, okay? And you run around the island one time in 3 hours, leaving gate 1 and coming back to gate 1 3 hours later, agree? Now I run around and it takes me 5 hours. How many hours are going to go by before we arrive back at gate 1 simultaneously? You arrive every 3 hours, I arrive every 5 hours, 15 hours. In 15 hours, we're both going to be back there, agreed? How many laps will you have made? 5. How many laps will I have made? But in multiples of 15, we will still be back there, agreed? We'll be back there together after 30 hours and after 45 hours as well, agreed? So if I pick a number such as 45, and 3 divides into it, which it does, and 5 divides into it, then 15 will also divide into it. So any number that divides both 3 and 5 will also divide their product. And the real statement is that if R mod P equals S mod P, and R mod Q equals S mod Q, if then it is true that R mod PQ will equal S mod PQ. So if the first two are true, then the third one will also be true. And the proof of that is the first mathematical proof that we've actually done in here. So fasten your seatbelts. And this is how mathematical proofs are done. Let's say that R mod P equals S mod P. That means that R mod P is R minus some multiple of P, agreed? That's what R mod P means? It's the difference between R and some multiple of P, agreed? Okay. So what is R? What is 41 mod 6? It's equal to 41 minus 6 times 6, agreed? So what is the nearest multiple of P that comes up to R? Is what the mod is, agreed? So you count up the P's until you're just below the R. So this is equal to the remainder, mod P, is R minus KP. Let's take an example. 41 minus 6 times 6 is equal to 5, agreed? So now let's take 53 mod 2. 53 minus 26 times 2, or 20. 26 times 2 is equal to 1. So this is our k, agreed? This is our k. So there's some multiple of p that approaches r but doesn't go over. So the highest multiple of p that's less than r, you subtract from r, and that gives you your modulus. So this can be written as r minus kp is equal to s minus h p, because they don't have to be the same multiples, agree? They're not the same numbers, they don't have to be the same multiples. Put everything on the left side, and we get r minus s minus k plus h times p equals 0. So that's a little bit of changing signs, putting them on the other side. Now, if h and k are both integers, then their product is also an integer. Their addition is also an integer. So this means r minus s minus, say, p, no, say L, no, yeah, say L, P equals 0. That means r minus s is a multiple of L. So r minus s is a multiple of P. R minus s is a multiple of P. That means the same thing as 15 is a multiple of 3, agree? R minus s is a multiple of P. So now let's try with Q. R mod Q equals S mod Q. Meaning R minus some numbers of Q, which is the modulus, equals S minus some other modulus of Q. And you can rearrange that, R minus S minus K plus H, Q equals 0. So R minus S minus L, Q equals 0. So R minus S is also a multiple of S, of Q. So now we've established by running around Okinawa Island that if R minus S is both a multiple of P and a multiple of Q, then R minus S is a multiple of P times Q, 15. So R minus S is a multiple of 15 of PQ. You gotta like your mouth to do this. R minus S is a multiple of PQ. That means R minus S minus some numbers of PQ is equal to 0. It's a multiple of PQ. So R minus S mod PQ equals 0. Now I'm going to start with a statement. And if you have any trouble with this statement, I want you to stop me. Because if you believe what I'm about to write, then you're going to be forced to believe the rest of the proof. Do we have anybody have any trouble with that? Well, speak now, or forever hold your peace. R equals R. All in favor? You're not sure?
I'm not sure.
Now,
I'm not
if
sure.
I subtract 0, minus S plus S, have I changed anything? I basically added 0 to it, agree? Minus S plus S is 0. Okay? So now let's just group it. R equals R minus S plus S. You know, as long as I do the same thing to both sides of the equation, it's still valid. And I'm going to take mod PQ on both sides. R mod PQ equals R minus S mod PQ plus S mod PQ. So I did the same thing to all three pieces, so it's a valid mathematical operation. And now, what did we establish about that? We decided that that was equal to what? Find it someplace. We decided that that number was
0.
Zero?
This number is 0. So if this number is 0, then the Chinese remainder theorem is established that R mod PQ is equal to S mod PQ. And we're going to use this, it's very important. So we established with all of that equalities on the board that if you're given that R mod P is equal to S mod P, and you're also given that R mod Q is equal to S mod Q, then it's always true that R mod the product is equal to S mod the product. Think of these as 5s and 3s and 15s. That's the Chinese remainder theorem. The last one, this is the last tool that we have to build, and it's called Fermat's little theorem. And if you have two numbers, A and P, that are not cofactors, in other words, P does not divide into A. That's a restriction. P does not divide into A. And as we found out an hour ago, we have to respect these restrictions. Then the following is true, that, and this is amazing, that A to the P minus 1 mod P will always be equal to 1 for any choice of numbers. So let's try a few examples. What I'm saying, as per an example, and now remember that P must not divide A. That's one of the restrictions. So if I have 4 to mod 3, that means I have to put a 2 up there. That's P minus 1, agree? So check, please, if that yields a 1. All in favor? Let's try another one. Let's take let's take 3 to the 4th power mod 5. 3 to the 4th power mod 5. 3 to the 4th power is an 81. 81 mod 5 is a 1. Okay, you guys want to challenge me for one? Fermat's last theorem, little theorem? So I'll give it a name, Fermat. So you guys pick an A and a P, and we'll write this prescription. The only rule is that this cannot divide into that. Otherwise, go. Give me one. So you want to work. Keep the numbers smaller. I'm over my
5 and 3.
5 what?
5 and 3.
5 squared mod 3 equals 1. P does not divide into A. No, this is,
Right. Yeah.
5 squared mod 3. 5 squared mod 3 is 1.
Yeah.
I get into my sleepies about now. I start-
25, 8 times 3, 24 minus
Thanks.
25.
It's not that I couldn't do it, I just can't do it at 7:15. Okay, you gotta see me at 10 o'clock. Okay, so we believe it's true by example. Now I'm going to show you why it's true by proof. And tell you a little bit about Fermat. This is a little theorem, not to confuse it with this last theorem, which is notorious in all of mathematics. Fermat was a lawyer who dabbled in mathematics at a fantastic level. And he would keep coming up with these little theorems that he would write in the margins of his diary and say, I do not bore you with the proof at this time, it's too long. And then he died. And there's lots of these around, and they've all turned out to be true. So it's not true. In that days, France, 200 years ago, as I remember, it was a real mortal sin to bore someone. That's the one thing that you could not do in society, was to bore someone. So he didn't want to bore you with the proof, So he just says, I won't bore you there. I think what was really true is he didn't want to bore himself. Because he just looked at these things and he said, well, it's obviously true. I mean, how can I really put down steps? You just look at it and know it's true. Well, his Fermat's last theorem was finally solved about 15 years ago after about 200 years of attempts, because he didn't bother to publish his own proof. I kept telling him to do it, he kept ignoring me. But his little theorem has the same thing. He didn't bother to show the proof, but a fellow mathematician found it in about 5 years. And this is the proof that he found. And it goes as follows. If I tell you that x mod 7 is a certain number, what are the only possible numbers that it could be? What are the only possible remainders you can get if you divide a number by 7?
0 through 6.
0, 1, 2, 3, 4, 5, and 6.
Everything else in the
Those are the only possible numbers you can get if you divide by 7, agreed? So those are the only possible numbers for mod 7. We recognize that. Now I'm going to investigate this equation, a to the p minus 1 power. And I'm going to develop my proof by making the following list of the multiples of a. 1a, 2a, 3a, all the way up to p minus 1 times a. So all I'm doing is making a list of the multiples of a. That's fair. Now for each one, I'm going to take a mod p for each one. And it's all going to be equal to something, mod p. Now you've agreed by my 7 that these all have to be in the set of 0 all the way up to p minus 1. They all are in the set 0, 1, 2, 3, all the way up to p minus 1. Just like the mod 7 was 0 through 6. Now the most amazing thing is that as long as p does not divide a, as long as p does not divide a, then every one of these modulus will be different from every other one. There won't be any duplicates. If this modulus turns out to be a 2, the 2 will not appear anywhere else. Each one of these modulus will be different from all the others. Each one will be unique. And that's totally to be unexpected. Why should each one not occur more than once? If this one occurs here, it will not occur for any of the others. Each one of these will only occur once. And of course, that's what Fermat saw as soon as he looked at it. He said, well, they're unique. Each one can only occur once. And a few years later, Leibniz showed us why each one could only occur once. Let's take 2 of these from the list. For the first one, let's take r, where r is some arbitrary number. r times a mod p. It's somewhere in this list, agree? R could be a 1, 2, 3, 4, 5, all the way up to p minus 1. Let's, for the moment, say that it does have the same mod as another member in the list, s. So take r and s. For the moment, let's say they do have the same modulus, and see what happens. Let's bring this to the other side. Ra mod p minus sa mod p equals 0. Now, by our first rule, and this rule of plus is also true for plus or minus, as always is, that means we can take the modulus before we do this, after we do the subtraction. So we get Ra minus Sa, and we can do the modulus p later. Now, clearly here we can factor out an a, so we get R minus S, a mod p equals 0, as before. And now, the product modulation means we can go backwards, or we can put the modulation into each factor. If we have the mod of a factor, we can put the modulation into each factor. So we have r minus s mod p times a mod p equals 0. Now, of those two factors, I maintain that this one is not 0. Or it's not 0 if p doesn't divide a. The only way this can be 0 is if p divides a, true? If p divides a equally, then it has 0 remainder, true? So now I'm going to restrict myself to cases where p does not divide a. As long as p does not divide a, this is not 0, but their products are 0, so this is 0. Now, if r minus s mod p equals 0, then it means that r minus s equals 0, because since both r and s are less than p, then their difference is certainly less than p also. So r minus s mod p is just r minus s. And r minus s equals 0 means that r equals s. So if you take two members from the list and assume they're different, they turn out to be the same. So this is what Fime left for us to prove. And then we established that every one of these members will have a unique modulus in the list of candidates. Every one will be unique. And there will be no repetitions, no duplicates. So now what I'm going to do is multiply this equation times this equation times this equation times this equation all the way down. And that is because products of equals are also equal, basic algebra premise. So that means that on the left side, I'm going to have 1a times 2a times 3a, all the way up to p minus 1 times a. And I'm going to take that to be a mod p. And on the right side, I'm going to have, and now we're neglecting 0 because it's 0 only if p and a are the same, which they're by hypothesis not. So the 0 is gone. So this is 1 times 2 times 3 times 4, all the way up to p minus 1, because they're all different and they don't repeat. So each one enters into the product only once. And now the rest is obvious, as the first of it was obvious also. I can factor an a out of every one of these terms. And I get 1 times 2 times 3, all the way up to p minus 1, times a to how many powers? How many a's are there? 1, 2, 3, p minus 1 a. Now I'm going to divide both sides by this. Now what do we produce on the right side?
1.
Anything divided by itself? 1. And on the left side these cancel and they leave the desired theorem. So we have proven this Fime's last theorem to be true. So Fime's last theorem is a to the p minus 1 mod p will always be equal to 1. This completes our tools, and now in 5 minutes and a few steps, we're going to show you why the technique that you used today is guaranteed to always work, using just these tools that are on the board. need to remind you where our private exponent d came from. So those of you that spent so many minutes of your life calculating d, can you remind me of the equation for d? 1 plus what? 1 plus k times p minus 1, q minus 1, divided by e, true? So Rick, is not that where all of those entries that you made came from? This is the equation for d. Now I'm going to cross multiply, a scary thing to do, and I get e times p is equal to 1 plus k, p minus 1, q minus 1. True. Now I'm going to remind you of some of the fundamental properties of exponents. And that is, if I have 3 squared and I multiply by 3 cubed, it's equal to 3 to the 5th, which means that a to the n times a to the m equals a to the n plus m. And another property of exponents is that if I have 3 squared and raise it to the 3rd power, it's equal to 3 to the 6th, which means a to the n raised to the n power is a to the n times m. So how many are seeing these for the first time? Don't raise your hand. Properties of exponents, well established. Now let's take our recovery of the key. We started with a key, and the first thing that those guys over there did was they raised it to the e power, true? The public exponent. And then they took it to the modulus of n, and they sent it over to us. Once we received it, the first thing that we did was we raised it to the d power and took another modulus of n. And we hope that that is going to give us back the key. And it did, many times. But why does this sequence of operation always give you back the key itself? Let's do a little bit of our properties of remainders. Here we have a d power outside of the mod. So the mod, the d can be put inside. So we have first the key. Can you teach me how to do it? The key to the ed, the d can come inside, mod n, and there's no sense taking another mod n because once you've taken a mod n once, it's not going to change, but I'll just leave it there for completion. And now I'm going to, and hopefully this will just be the key. And now I'm going to replace ed with the only thing it can be equal to that makes this work. The ed must be equal to that. So what we have is the key to the power of 1 plus k, p minus 1, q minus 1, mod n, and another mod n if you care to. And this is what we're evaluating. Now, according to our properties of exponents, then that 1 plus something can be broken into 2 pieces. So what we have is the key to the first power, and then it's times the key to k, p minus 1, q minus 1, mod n, mod n. Now, the key to the first power is what we want, agreed? So we will be left with only the key to the first power if by some miracle this which is in the box is equal to a 1. If that which is in the box is equal to 1, then we're only left with the key by itself. So let's investigate whether what is in the box is equal to a 1. We have the key to the power k, p minus 1, q minus 1, mod n. Now we want to evaluate this. Now, you remember that n was carefully selected to be pq. So I'm going to rewrite this as the key to the power k, p minus 1, q minus 1, mod pq. And I want to evaluate what that is. And I'm going to do it in two pieces. The first piece is I'm just going to do the p. And then the next piece, I'm just going to do the q, one at a time. And this is going to lead us to using the Chinese remainder theorem 3 and 5. So let's take the key to the k, p minus 1, q minus 1. First, let's do mod p, see what it comes out to be. Now, if I have 3 exponents multiplying themselves, as I do here, then you can break it to one inside the parentheses and one on top of the parentheses. The rules of exponents. So this can be written as key to the p minus 1, and this whole thing is then raised to the what's left, the k, to the q minus 1 of mod p. Now, according to our rule of powers of modulus, the modulus can be taken inside. So I have key to the p minus 1 mod p, and that whole thing is raised to the k q minus 1. Raise your hand if you see something familiar about what's in the bracket. Raise your hand if you see something familiar about what's in the bracket. What's it equal to? 1. Thank you, Fima. What's in the bracket is equal to 1, agreed? So this is equal to 1 mod p. Now I'm going to do the same thing with q. Key to the power q minus 1, the whole thing raised to the power k. Well, I didn't do the outside powers yet, so that's another step to take. So what is in the bracket is a 1. So I have 1 to a power k q minus 1. Well, what's 1 to any power? Still 1, agreed? 1 squared, 1 cubed, it doesn't matter. So this is 1 mod p. Now I'm going to do the same thing with q. So we have the key to the q minus 1 power, and then that whole thing is going to be raised to the k p minus 1, and now it's going to be mod q. So that becomes key q minus 1 mod q, and the whole thing is k to the p minus 1. Now, raise your hand if what's in the bracket looks familiar. So this is equal to 1 to the k p minus 1, and 1 to any power is 1. So that's 1 mod q, which is what we're doing. So we have established that the key to the power of, before we separated it out, it was k, q minus 1, p minus 1. We've established if you do this in mod p, then you get 1 mod p. And we've established if you take the same quantity and you do it a mod q, then you get 1 mod q. And what does the Chinese remainder theorem tells us? That if this equals that mod p, And if this equals that mod q, then this equals that mod p times q. Meaning that e to the k, q minus 1, p minus 1, mod pq equals 1 mod pq. Now, compare what is in the box there to what is in the box here, or what is up here. This establishes that this is equal to a 1 mod pq, or equals 1 mod n. So everything in the box here indeed is equal to a 1. That means that everything up here equal to everything down here, but down here is just a 1 times the key. So this is only a 1, and what's left is the key. So this equals the key. QED, as we say in the proof. Now, what were the key beams upon which this rested? The key beams upon which it rested was that n must be a product of two numbers, p and q. So that was one of the conditions that we met. The other is that D must be formed as 1 plus k, p minus 1, q minus 1, over E. If we form D in this fashion, do you see the p minus 1 and q minus 1 coming into it? And once they come into it, then Pimo's little theorem takes hold and turns them into 1. So the only way that they're going to be turned into 1 and give you back the original key is if you choose your private modulus to incorporate p minus 1 and q minus 1. If you do that, then you guarantee that the D that you arrive will reverse the E that you sent out there. Aren't you glad you stayed? You wanted to see it, so now you've seen it. And you can say, I saw it, I stayed. The others didn't stay, but I stayed, and I saw it. So congratulations, you saw it. You may not be particularly in love with mathematical proofs, but you've seen one and stepped through one, and to whatever degree you did, followed one. So welcome to mathematical proofs. Just establishes. So now, not only do you know that public key, private key encryption works because you know the rules to follow to get your D and to get your E, and you can practice it and do it any time, but now you understand why it always has to come out right. So get a good night's sleep, and we'll leave it there.
Well, so, just wondering, so this is the sender, the receiver, okay, and they've done all this, but what about if you just have like data somewhere, you know, in your computer? Do you have to do all of this?
There's no need to do it all for yourself if it's all in your computer because it's not exposed and the bad guys can't see it. But if you do encrypt the data in your computer, it should not be necessary to be as strong as a public key encryption in the sense that there's no transmission, nobody to pick it up. And you can probably just use the old-fashioned symmetric key where you encrypt the data according to a simple key that you pick, like 6.5, and you store that 6.5 in its 6.5 form, and you use it to decrypt it. But if you're really insecure and paranoid, then yes, you can choose a N, P, and Q, and you can encrypt that, but all of that encryption information is going to be right next door in your own computer to the key that you had a moment ago. Unless you throw it away, then you'll forget what it was and you can't undo it yourself. So yes, you can do it. Question is, I'm not sure if you want to do it, but yes, you can if you choose to. Absolutely right. Good question. Questions, others? Thank you very much. So the tape will be out there, and if you want to have the link mailed to you, you haven't had enough, and then put your email email address in the sheet, we'll be sure that the link goes to you.
You have my email address.
Guys, I haven't,
I do have your
sent out a
email
message
address.
on my emails.
Do you want it? You want the
Pretty
link?
late, where's it gonna go?
Well, Jack's place is open until 9.
Yeah, I'll just post it.
There's a new Domino's.
The beginning. Or just, Sam's by the Sea again?
What was that?
Sam's
Sands by the Sea, I'm always glad to go to Sands by the Sea.
Yeah, I wouldn't mind, I'm going there when my wife gets there.
Oh, yeah.
But yeah, I haven't eaten yet, so I want to.
She loves to sit there with the bill of the lobster and, tear it apart.
All right, let me send out a message to you. Sounds good, I can go for Sam's.
1830?
18:30, we'll meet right here. No, 18:30 over there. We'll take off from here at about 8.
Oh, you're talking about tomorrow?
Yeah, tomorrow.
Oh, tomorrow, oh, yeah, okay.
For Saturday. Yeah. Tonight, I gotta catch them up.
Okay, all right.
The other one's kind of in college, so she doesn't really analyze it.
Oh, yeah, this is the paper if you want them to get the original. I should have did that, I'll put the reference out there. But this is everything that I did, just with the RSA, shipper system, and
Okay, I will.
everything's there. And it was fun. Pleasure having them. It's number 3. This is it, boy. It's nice to have you there and do that.
Did I tell you my social experiment
Last year? Yeah, I think you mentioned you had one.
It's really simple.
There should be, knowing him.
There's a formula that describes all of the
Let
differences
me go get some.
between consecutive exponents.
That's the type of thing he does, yeah.
And it can't be reduced to I times IDN minus 1.
You're too humble to publish? That's what all
Well,
geniuses.
actually, well, it's not just that.
They don't care about publishing.
I've never published anything. I was gonna, we were planning when I was doing philosophy.
See you tomorrow.
Well, noontime,
At Palo Alto, to start working on joint publications, and then our chair got pulled away to be the whole section chair rather than just our department chair. And so we never got around to working on developing publications. So I've never been with anybody.
A simple
who
solution
mentored
to
me
be much last clear and would be earth shaking. You might even be leaving us behind, soaring in the stars. Oh, really? Maybe you don't want that kind of fame, I don't know, but that's what you would have. No, you can't show it to me on my phone now. Next meeting.
But it is that simple.